Buttery Game Theory present the Mastering Advanced Game Theory Episode 1. Nash Equilibrium in Multiplayer Games. What happens when more than two players interact in a game? How do we find the Nash equilibrium when everyone is trying to maximize their own payoff? Here are what we'll learn today. Understanding how to extend Nash equilibrium concepts to three-player games. Learn how to construct and interpret payoff matrices. How to solve for pure Nash equilibria. What is a pure Nash equilibrium? A Nash equilibrium is a stable state where no player can improve their payoff by unilaterally changing their strategy. In the Fundamental series, we learned how to find a Nash equilibrium for two players. For games with more players, the concept remains the same. In an X-player game, where X is the total number of players, a pure Nash equilibrium occurs when all X players are simultaneously playing their best responses to the strategies of the X-1 other players. Let's consider a prisoner dilemma as our three-player game example, involving Alice, Bob, and Carol. Each player has two possible actions: cooperate or defect. Their payoffs depend on the combination of actions chosen by all three players. For this example, we assume that all three players know what the other's payoffs are. To construct the payoff matrix, let us first define the columns for all the players and for the payoffs. Since there are three players, each with two possible actions, we will need 8 rows, from 2 to the power of 3 possible combinations. Now assign all the actions combinations for all players. Lastly, assign the respective payoffs for each action combination. With this payoff matrix, we can see that if Alice, Bob, and Carol cooperate, each of them will get 3 as their payoffs. Meanwhile, when Alice and Bob cooperate, while Carol defects, Alice and Bob will get 1 while Carol gets 4. If you have any question, feel free to ask it in the comment section. Now let's move to the next step. To find the pure Nash equilibria, we need to analyze each combination of strategies. Let's start with Alice's point of view. When she thinks that Bob and Carol will both cooperate, Alice has two options: cooperate or defect. If she chooses to cooperate, she'll get 3 as payoff, while when she chooses to defect, she'll get 4. Therefore, when others cooperate, her best response is to defect. When Bob is cooperating and Carol is defecting, her best response is defect. When Bob is defecting and Carol is cooperating, her best response is defect. And when Bob and Carol are both defecting, she should also choose to defect. So we have the preference of actions for Alice in every scenario of actions by Bob and Carol. In total, her preferences of action is 2 to the power of 2 equals 4, since there are 2 other players to be considered. Now for Bob, when he thinks that Alice and Carol will cooperate, his best response is to defect. Repeat this process for all other combinations. And we got the 4 best responses for Bob, also the 4 best responses for Carol. Now pause the video and try to find the Nash equilibria on your own. Can you guess what the Nash equilibrium is? To identify the Nash equilibria, we just need to look for the combination that is preferred by all players. Which is this one, where all players defect. That is the only pure Nash equilibrium. We see that though this combination, where all players cooperate, produce the best outcomes for all players, it is highly unlikely to happen, because all players have an incentive to defect. So today, we learned how to extend Nash equilibrium concepts to more than 2-player games. We constructed a payoff matrix, analyzed each combination of strategies, and identified the pure Nash equilibrium. If you found this helpful, give it a thumbs up and subscribe for more game theory lessons. See you in the next episode, where we'll explore how to find Nash equilibria when players have multiple actions to choose from.